let's say I have a mass of 1. 10 over 1 would give me an acceleration of 10. But what if my mass is 1,000? I have 10 over 1,000. My acceleration is much, much, much lower. So the bigger this mass is, the smaller the acceleration is.
So if the force is higher, then it accelerates.
Yeah, absolutely. Good, 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 good. So this tells you that the acceleration goes up when the force goes up, and the acceleration goes down when the mass goes up. Now, these equations, I know that you guys aren't going to deal with these equations in the classroom. And I know that this is a little bit, it's a little bit complicated to be looking at it this way, but I wanted to introduce some of these simple equations to you so you can think about, let's move on though to maybe, let's move on to maybe a little more intuitive way of thinking about these concepts. So what do we mean by net force? We talked about this last time. What do we mean by net force?
All of this. You do.
What do you mean when you say net income? What's your thought? Yeah. Right. You have negatives, positives. And the net force is the sum of all the forces on an object. Okay. So you might have a bunch of forces on an object. You might have forces coming from all different directions. And what you're interested in is understanding when you add all those up, what's the net force on an object. Remember we talked about this last time. If I put I've got my table here, and I put a ball on top of it. Let's think about this ball. What are the forces on this ball? It's got some mass.
Well, nothing yet, right?
Gravity, the force of the table. The net force is nothing, but there are forces acting on it.
All right, so we had a couple of things. Somebody said gravity, but what's the force on what?
The force.
So the language. So here's where we got to be precise with the language. How do we describe the force of gravity on an object? What do we call that?
What do you call
Yeah,
that?
weight.
Yeah, I was going to say that.
So there's weight.
The force of my gravity.
Yes.
Thank you.
What else? What other forces are on that object?
The table.
Right.
But it is in the sense of physics. It's pushing.
Like personification.
It's personified, absolutely.
So, what's the net force on this object?
Bird, he asked the question you just asked.
What's that?
Just say what she said.
She said it. What's the net force on the object? Say it. You said it already.
Zero.
Zero.
How do you know it's zero?
Because nothing's happened. That's what I'm
That a
thinking.
girl.
That's right. Here, so let me. I know this equation.
Back in the game.
I know this equation is scary. I know this equation is
Yes,
scary.
it was, Mike.
But look.
My son said.
I know it's scary, but what you just said is right here in the equation. There's no force. This is zero. Therefore, this is nothing's happening. So you said nothing's happening. Therefore, the sum of the forces must be zero. Okay.
That's what I said.
You got it.
Good
You
girl.
got it.
And when you have
All
the
right.
zero in the numerator, what is it?
So let's talk about. So I don't want to go too far. But I want to get you guys to working on a fun project here in a second. But here's how to use. I'm going to give you some simple tips. All right. This is actually what we do with introductory physics class, and of course we go into much more detail. But I want you to think about how to use Newton's second law. Here's how to properly think about that Newton's second law. Because really you do have, this is, although I've written the equation down, you don't necessarily have to think about it in terms of mathematics, but you do want to think about it in terms of the relationship between these three things: force, acceleration, and mass. The first thing you want to do if you want to figure out a problem like this is to draw a picture. You want to draw a picture of your system, a car, again, a chair, a table, a roller coaster. Draw a picture of it. The second thing is probably the most important thing. This equation only makes sense if you are very consistent on what object you're talking about. All right? In this problem, we've got a table and a ball. All right? If we start confusing the two, what are the forces on the table? What are the forces on the ball? Are we talking about the ball and the table? Are we talking about the table? You have to say, okay, I'm talking about the ball, or I'm talking about the chair, or I'm talking about the car, whatever object. You have to be very precise about which object you're talking about. Okay? Otherwise, you'll completely confuse yourself. So that's important, but it's simple, right? You can just choose which object you're talking about. And then you want to identify the forces that are on that object. Okay? And that's really all there is to it. And then you ask yourself, are those forces in balance? And that's what we just got the right answer over here. We identified this object. We talked about the forces on that object. And we decided that, are those forces in balance? Yeah, they're in balance.
Are you saying in or on?
In.
No, they are in balance.
They are
balanced.
They are
Okay.
equal.
Should she have used that word equal? They're equal?
Yeah,
That's,
well,
well.
Sorry.
there could be many different forces. They all add up to being zero. In this case, they're equal and opposite, right?
Because if they were
All right, and then the fifth thing, if there is a net force, then the acceleration will be in the direction of that net force. Okay? So let's just do one quick example, and then I'll shut up and let you guys have fun. So let's look at this situation. You've got a box sitting on the Earth.
Is this M stand for mass?
Yep, M stands for mass. So we have M1, M2, M3. Okay? What are the forces? Okay, so this is kind of a trick question. Is this a well-posed question?
depends on what you're talking about.
So what do you mean?
So is it the force on M1, the force on M2, or the force on M3?
Exactly.
Because you have to be precise.
That's right.
Okay.
That's right. Otherwise we're going to completely confuse ourselves. So we have to, before we can use this idea of force, acceleration, and mass, we have to be very precise on which part of this picture we're talking about. Now you can choose. You can choose any one of them, and you can also choose one and then go back and then choose the other. But what we want to do here, let's say M2. What are the forces on M2? I'm kind of giving you a hint here. What are the forces on M2?
It's mass, or weight rather.
Okay, so M2. So we have one vote for so its weight, which M2's
force
weight.
of gravity.
Okay, so M2 has its own weight. That's one of the forces on it. What else?
Oh, which one, M3 or M1?
Okay, hold on. So let's start over. What are the forces? One way to do this is to be the mass. I'm the mass. What's happening to me? All right. What are the forces on M2? Yeah. From the ground. Pull the ground. Yeah. So there's a force from the ground. What direction is it in?
Up.
All right.
Opposite.
We said the weight, so we have the force from the ground, we have the weight. Which direction is the weight? Okay. What else we got? Well, does it count?
I mean,
What did you say?
M1, let's push it down into.
Absolutely. I agree with you. Now see, okay, so this is what might be confusing to you. You might be saying, well, didn't you say you got to choose the object? But you got to think of, what you're doing is you're saying, what is affecting M2? Okay. The weight of M1 is affecting it too, but what you're worried about is what's affecting M2. And that weight of M1 definitely is a force on M2, right? Okay.
But wouldn't that just be kind of balled up in the net force of M1? Rather, like, would you really, if you're talking about only M2, would you really consider M1's weight as well as its force? Or would you just call it force because you're only talking about its net force? in that system.
I'm not sure I'm understanding precisely what
Okay,
what
I'll
you're
think about it
thinking.
and say
Wait.
it a different way.
You really want to think about it in the simplest way. If you're
Yeah.
M2, you don't really know anything about where that force is coming from. All you know is there's a force there.
Right, that's what I mean. Like, but you wouldn't call it. You don't
Yeah.
want to call it. You
It's
don't want
a
to.
force, and its force is equal to...
Right. You don't want to say its weight and its force and whatever else.
Right,
You
you
just
only
want
count
to
it
call it
once.
its. Right.
You
Okay.
only count it once, right?
Yeah.
So from M2's perspective,
Oh, sorry. That was a force thing. Sorry about that.
so from M2's perspective, there's sort of three different forces here. There's the weight of M1, there's the force of the ground pushing up, and there's its own weight, okay? So there's the weight of M1, the weight of M2, and the balancing force, or normal force. You can just think of it as the balancing force from the surface.
How come you can't just call it the force of M1?
Because
That was my question.
You could. It's the force. There's a force from M1 that happens to be equal to its weight.
Okay. Since it's not moving, it is the weight. Okay.
That's a good point. That's a very good point. If we were in an elevator and things were accelerating, there would be much more
wouldn't.
complicated.
Okay.
Okay.
Yeah.
on accelerator.
So
You're right. In this
appropriately
particular
termed
situation,
weight of M1, or would you just call it the force of M1?
you could say that what you could say is that it's the contact force or the normal force of
Okay.
M1 on M2, and it so happens to be equal to the weight in this case.
And when we're talking to kids, it's the force of M1.
Yeah, that would be probably the best way of saying it. Yeah,
Okay.
I agree with you.
I just want to know how to talk about it.
No, you're absolutely right.
Not
The weight, it's equal to the weight in this case just
because
because
of what's going on.
everything's stationary.
Okay.
So, can we set something? Can we relate any of these forces to each other? What do we know is a balance here? Or do we know that are the forces balanced on
They must
M2?
be. Yeah.
Well, I mean, you can't really answer that question precisely because you don't know. It's just a snapshot of something. If everything's stationary, are the forces balanced?
They must be, yeah.
Yeah?
Mm-hmm.
Yeah, okay. So what does that tell us? So this is all the forces on M2. If the forces are balanced, that tells us, what can we say then about this weight and this weight and this?
The balancing force is equal to weight of M1 and M2.
The balancing force
Oh,
is equal to the weight of M1 and M2.
Mm-hmm.
Is everybody in agreement with that? See, if I ask that question a different way, you guys would all get it right. If I had a scale there, if I had a scale sitting underneath these, what would it read?
Their weights
It
combined.
would read the weight of M1 plus that weight of M2, right? That's what this red arrow is. Okay? All right, I think I've tortured you guys long enough. So what we're going to, yeah.
I want to ask you something. You can tell me, no, I don't want to go there yet.